2016, Pharma Research Products Company Limited launched the Rian eye drop. Rian eye drop is an over-the-counter eye drop that contains PDRN that treats micro damage of the eye from the contact lens usage. In this video, we from Team 135 will present our proposed overall production process of Rian eye drop. Here is the list of ingredients we propose for Rian eye drop. We will explain the functions and reasonings for using these ingredients in the next slide. In this table, we include ingredients quantity per unit as well as quantity per batch. The active ingredient of Rian eye drop is sodium polydioxyribonucleotide, which has anti-inflammatory and cicatrizing effects on the eye's tissue. Because it's a ribonucleotide, it's fairly unstable in the presence of metallic ions. To combat this problem, use the sodium-edited dihydrate as a chelating agent. To avoid irritation and soreness from direct contact with the eye, the drug must be as acetonic as possible. Therefore, a tonicity adjustment agent sodium chloride is used in this formulation. Thickener polyvinyl pyrrolidone is also added to increase viscosity and give a good retention time for the drug on the eyes. pH is also an important aspect of eye drop. The drug solution's pH is adjusted to the tear's pH, which is 7.4, so it won't be painful when administered. The pH is adjusted using HCl or NaOH and is maintained stable around 7.4 using phosphate buffer. Finally, because eye drop is a sterile preparation, we use water for injection as solvent. Through research conducted, it is observed that none of these ingredients is thermolabile nor incompatible with each other. To ensure sterility in the eye drop production, EU, FDA, WHO, and the rest of the world established GMP of sterile medicinal products. In this case, we choose to adopt EU GMP. There are several important criteria for sterile production. The first is area grade classification for each production process. According to EU, there are 4 grades of clean rooms which are grade A, B, C, and D. These grades have different environmental monitoring such as for airborne particles, microbial contamination, and air control, which all will be explained in detail later. Another important factor is personnel and material flow. Personnel and material flow should be outlined clearly and be separated to minimize contamination. Based on those important criteria, we design and propose this production flow plan. The overall production starts from warehouse raw material and ends in product storage. Then, transferred through dynamic pass-through or DPT, the final products will go to warehouse and product. Also added here are the QA and QC divisions, which will increase the efficiency of the workflow as it allows faster and easier communication during the production process. As shown here, each grade is colored differently to ease recognition between grade. The requirements for each room will be explained in depth later. Flow of material is shown by the blue arrow, starting from loading dock through the MAL or material airlock in and out. Flow of personnel is shown by the red arrow, starting from gowning room through the PAL or personnel airlock in and out. Both of them are separated to minimize contamination. A curved blue arrow shows the air movement. In sterile production, we can use the principle of air moving from high pressure to low pressure to minimize the risk of contamination by designing the differential pressure between each grade and unclassified room. Now let's talk about the room requirement. First is the airborne particles. This table shows maximum permitted airborne particles per cubic meters adopted from EU GMP for different room grades. Airborne particle must be monitored because the presence of particles in the eye drops can irritate the eyes. This table shows recommended limits for microbial contamination adopted from EU GMP for different room grades. The limitation of microbes are placed to ensure that the products will remain sterile. This table shows the air control requirement for each grade room. Note that there is no specific value of pressure for each grade room. Now that the manufacturing plant layout and requirements are done, let's move to the production protocol. Every Rian eye drop starts in the warehouse of raw material. This is where the API, excipients, and equipment are stored. After taking all of the needed ingredients, we move to the weighing booth, a grade D room, where all ingredients are weighed to make one batch. Next, all of the ingredients undergo mixing in mixing room, a grade C room. First, certain amount of water for injection is put into mixing tank A, then APA and other excipients are added into mixing tank A to be dissolved. Next, to activate PVP, PVP is added to mixing tank B containing a certain amount of water for injection. After all components are thoroughly mixed in both mixing tank A and B, PVP solution from mixing tank B is mixed into solution in tank A. Then, the volume for mixing tank A is added with water for injection until 80% of the desired volume to undergo IPC. The solution pH is adjusted to the Thiers's pH using NaOH in HCl solution. After the pH is adjusted, next is moving on to grade A room. Firstly, the solution in mixing tank A is added with water for injection until the desired volume. Then, the bulk solution undergoes filtration and filling into the eyedroppers. Then all the containers are sealed with sealing machine. After that, all the containers undergo terminal sterilization with autoclave in grade C room. When terminal sterilization is done, the products will be evaluated, packaged and labeled, and will be stored in the end product warehouse. It's possible to get contaminations other than from raw materials. These sources of contaminations can be obtained from the personnel, equipment, and environment. Some actions and policies can be implemented to prevent these contaminations, such as the employee should be qualified, well-trained, and in adequate number. Each personnel should be trained for the latest skills required in order to minimize contaminations due to poor performance. They have to be in a healthy state which is free from diseases that may contribute to contaminations. Good sanitation practice is necessary, and protective apparels should be worn properly. Particulate matters can be obtained from the equipment. Thus, any instruments and utensils should be cleaned and monitored regularly. Disinfectant can be used to clean these equipments. Plastic containers can be pre-sterilized by multiple water for injection rinses to prevent pathogen contamination. To prevent contamination from the environment, regular monitoring can be done. Some examples of monitoring methods are surface monitoring, active air monitoring, and passive air monitoring or settling plates. These methods provide information of microbial quality of the environment. Records of manufacturing history can also be used to identify errors in the manufacturing process. Sterility is an essential parameter for ophthalmic products. Considering that all of the ingredients, including the active ingredient and propylene plastic primary containers used, are thermostable, terminal sterilization is chosen. This type of sterilization provides the best sterility guarantee compared to other sterilization methods. Before the terminal sterilization, filtration is needed to minimize the bioburden and particulate matters after the compounding process. Next, moist heat sterilization can be performed using autoclave at a temperature of 121 degrees Celsius for 15 minutes. To make sure the products are sterile, in-process control and final evaluation should be conducted. Evaluation is essential for an eye drop to ensure its quality, safety, and efficacy. We will look at 10 attributes that are necessary to be controlled and evaluated for eye drop product. Identification of the API can be done using UV visible spectrophotometer. Here is the accepted spectrum characteristic from the dosage form tested. UV visible spectrophotometer can also be used for assay with the help of several external standards to create a calibration curve. Here is the accepted assay criterion for one individual unit tested. Appearance can be evaluated just by visual inspection with the help of black and white background. Here is how the dosage form solution should look. To evaluate the number of particulate matters in the dosage form, several tests from USB section 789 particulate matter in ophthalmic solution can be done. The accepted criteria can also be viewed there. pH can be tested using pH meter. To ensure comfort when used, here is the accepted pH range. Osmolality can be checked using osmometer with the accepted osmolality for one individual unit as follows. Sterility can be tested using membrane filtration test according to USP. Under this test, the product must give sterile result. Deliverable volume can be tested according to USP under section 689 deliverable volume. Here is the accepted criterion for all sample tested according to USP. Container of eye drop can be evaluated visually or when undergone tests such as upside-down tests for several minutes. There should not be any leakage. Viscosity can be tested using viscometer special for small volume sample. Here is the appropriate viscosity range for one individual unit tested. We finally come to the end of the presentation. This is the overall proposed production process of Freon eye drop from our team, Team 135. Thank you for your attention. 지금까지 들어주셔서 감사합니다.